Hi everyone, welcome to the talk. My name is Xiaohong Chen. I'm a fifth-year PhD student at the University of Illinois. Today, I'll introduce a unified proof framework for automated fixed-point reasoning. This is a joint work with Minh-Thai Trinh, Nishant Rodrigues, Lucas Peña, and Grigore Roşu. Our motivation is fixed-point reasoning. Fixed points are everywhere. They are used to describe inductive data structures on heaps, properties about infinite streams, term algebras, temporal properties, and the function correctness of programs. However, there is no unified proof framework that aims to support the automated fixed-point reasoning in all the above areas. So in this work, we propose such a general unified proof framework for automated fixed-point reasoning. The foundation is a base logic equipped with a set of generic proof rules for automated reasoning like fixed-point reasoning, frame reasoning, context reasoning, first logic reasoning, and domain reasoning supported by the SMT solvers, etc. In this base logic, we can define other logical systems as logical theories like separation logic, first logic with least fixed points, the theory for linear temporal logic, for reachability logic, and so on. The proof framework applies the generic proof rules to the given logical theory, and the result is a specialized automated prover for that logic. Note that the proof framework is generic because the same set of proof rules is applied to all the logical theories that we use to instantiate the framework. This makes our proof framework different from the existing proof system that are designed specifically for one area or one domain, such as the separation logic provers, the LTL provers, etc. And finally, the proof framework implements some proof strategies and proof search heuristics. These strategies are also generic and can be applied to all the logical theories. A question here is, what base logic should be used in this architecture? In theory, any logic that has the expressiveness to encode other logical systems as theories and has a fixed set of proof rules can be the base logic. And in this work, we choose matching logic. So what is matching logic? Matching logic is a very expressive logical system. As shown on the left, many important systems such as first logic with least fixed points, separation logic, temporal logics, reachability logic, Hoare logic, and many more can be defined as logical theories in matching logic. Therefore, if we have an automated theorem prover for matching logic, we can instantiate it by the various logical theories and obtain various specialized theorem provers as shown on the right. So what is matching logic? Due to time limit, I cannot show you the formal definition of matching logic, but only some intuition. You can find all technical details in our paper. In short, matching logic consists of three components: the syntax, semantics, and a proof system. On the syntax, matching logic builds formulas, which we call patterns. Patterns can express structures, logical constraints, quantification, and fixed points. In some sense, the syntax of matching logic combines the first logic syntax of terms and formulas, which gives us more flexibility. On the semantics, matching logic has a pattern matching semantics, and this is the core concept in matching logic. It means that the semantics of a pattern is the set of elements that can match it. Here, we list some examples of matching logic patterns to give you some intuition. The first pattern is cons of x nil. It is a pattern matched by a list of only one element x, so it's like a first logic term. The second pattern is a separation logic formula. It is matched by those heaps where x maps to y and a singly linked list starts at y. Note that this pattern can be matched by several concrete heaps, and if we don't care the value of y, we can quantify it, as in the third pattern. The next one expresses a temporal property like in LTL, and the fifth pattern builds a computation configuration where there is a while loop running on a program state. The last pattern captures a correctness property. The meaning of these patterns is determined by the logical theories. The patterns about heaps are within the theory for separation logic, for example. And to conclude, in matching logic, we can have a uniform representation of the properties from various logical systems. Besides the syntax and semantics, matching logic has a Hubert-style proof system. However, that proof system is not suitable for proof automation because it gives us too much freedom in proof search. For example, there are two rules in the proof system, the modus ponens and Konos-Totowski. The modus ponens rule requires us to guess a premise phi. The Konos-Totowski rule requires the left-hand side to be a fixed point, which doesn't always hold in practice, like in this example. In practice, fixed points often occur within the context. So a main challenge for us is to find a new set of proof rules for matching logic that are more deterministic and can deal with context. Just to show you the big picture first, this is our proposed proof framework. It has 11 rules that handle fixed points, context, the standard first logic reasoning, and so on. Due to time limit, I'll focus on the fixed point and context rules, and the rest proof rules are explained in our paper. Firstly, we recall the famous LFP rule based on Park induction. This rule lies at the core of many proof systems for induction or recursion. Formally, if there is a recursive definition P, and our proof goal is P of X implies psi, then we can reduce the proof goal into M subgoals, whose left-hand side are obtained by unfolding P and replacing all the recursive occurrences of P by the right-hand side. And clearly, this rule allows us to prove the separation logic property like LL of XY implies LR of XY, where these two are two equivalent definitions of list segments on the heap. And since the left-hand side is already a standalone fixed point pattern, we can apply the proof rule L of P directly. The limitation, however, is also clear. If the left-hand side is not a standalone fixed point, the L of P rule cannot be applied. And here we give two such examples where the fixed points occur within a context. The first one is from separation logic, and the second one is from program verification. The proof rule L of P cannot be applied to prove these properties, so we need a way to handle context. Now, let me explain our context reasoning rule using this example proof goal. LL of XY star list of Y implies list of X, where the fixed point LL of XY occurs within a context. We use a proof rule called wrap to wrap the context on the left-hand side and move it to the right. The new proof goal becomes this. LL of XY implies this pattern. Intuitively, this new pattern is the set of all heaps H that satisfy the property H star list of Y implies list of X. In other words, it is a set of heaps that satisfy the original right-hand side list of X if they are plugged into the context. We call this above right-hand side a contextual implication. And using that, we can rewrite the proof goal into this. LL of XY implies C contextually implies list of X, where C is the yellow context in which the fixed point occurs in the original left-hand side. After the application of the wrap rule, the left-hand side becomes a standalone fixed point, and we can apply the proof rule L of P in the usual way. Contextual implication is a main contribution in our work. It gives us a systematic way to handle all context. Formally, let C be a context and psi be a pattern that represents a property we want to satisfy. The contextual implication is defined by this pattern matching, matching logic pattern, whose semantics is the set of elements X such that C of X implies psi holds. In other words, X satisfies psi if within context C, and this is why we call it contextual implication. The key property about contextual implication is wrapping and unwrapping. In short, if we want to prove C of phi implies psi, we can move C to the right-hand side and prove that phi implies the contextual implication. Now, suppose phi is a fixed point, we can apply the proof rule LFP to do inductive reasoning. And the result is several new goals whose right-hand side are the same contextual implication and the left-hand side are obtained by unfolding the fixed point phi. And at that time, we can unwrap the context and move C back to the left-hand side and keep going with the reasoning. So what's interesting here is the context C can be any pattern. It can be a heap context, it can be a configuration context, it can even be a logical constraint context. This makes contextual implication and its wrapping unwrapping rules very general. In separation logic, there is a construct called separating implication, also known as the magic wand. The magic wand is a special case of contextual implication. Indeed, if we let C phi be this context about heaps, then the magic wand is the same as the contextual implication semantically. And also, the proof rule ADJ in separation logic is a special case of the wrap-unwrap proof rules. Contextual implication is a main reason why our generic proof rules really work in various logical theories. It is very general and it captures the essence of context reasoning. We evaluated our unified proof framework on 4 logical systems. For separation logic, we took the separation logic competition benchmark and we passed 265 out of 280 tests, which outperformed many separation logic provers. For LTL, we proved the axioms in the complete LTL proof system. For further logic with least fixed point and reachability logic, we proved the function correctness of a simple program that computes a sum from 1 to n. And during the evaluation, we also noted several bottlenecks that require future research. The first is non-fixed point reasoning. In our current implementation, we didn't pay much attention to it, and we plan to improve it in the future, including more powerful first logic reasoning and equational reasoning. The second is to design smarter proof strategies and proof search heuristics. In the current implementation, we use the simplest bounded depth-first search algorithm. Using a smarter heuristic allows us to terminate the proof search sooner and thus improves the performance of the prover. To sum up, we are pushing towards a unified proof framework, and in this work, we focus on automated fixed point reasoning. Using matching logic as the base logic, we can define other logical systems as logical theories and get a prover for all of them. The main challenge is how to handle fixed points that occur within a context. To solve that, we propose a generic context reasoning module and the concept of contextual implication. We evaluated the effectiveness of our proof framework using 4 different logical systems and have obtained promising results. Our work shows that a unified proof framework for automated fixed point reasoning is indeed possible in practice. That's the end of my talk. Thank you for listening, and I'm happy to take some questions from you.